Hello, in this video we are going to calculate the moment of inertia, this time of a solid cylinder about a perpendicular axis that passes through the center of the cylinder. In a previous video we calculated the moment of inertia of the solid cylinder about the z-axis. So in this video we are going to calculate the axis we will be considering here will be the IX axis. And due to the symmetry, the cylindrical symmetry of the cylinder, okay, Ix is going to be equal to Iy actually. So we are going to make use of the result we got in the previous video, so Iz, to do our calculations. Okay, so here we are having a cylinder of mass m, okay, it has a radius of capital R that I've illustrated here. So we want to calculate here Ix and Iy, because Ix is actually equals to Iy due to the symmetry as I earlier mentioned. So Ix is equals to Iy due to symmetry of the cylinder. So Ix, so just to emphasize on the axis that I'm using here, I have z that's in this direction, I have x that's upwards, and I have y that enters actually into the paper. Okay, I just decided to represent it like that so that you can kind of picture out what's happening. So the idea, as usual, is to be able to isolate an element, okay, that can enable us to generate the symmetry of the solid figure we are working with. So in this case, you're having a cylinder. If you take a very thin slice of that cylinder, you're going to have a disc. So this element, our element here is a disc, okay, of thickness dz, very, very tiny thickness. So what we can do already as a first step is to calculate the volume, the mass per unit volume. So if we denote rho, the uniform volume mass distribution, then rho is going to be the mass of the cylinder all over its volume, the volume of the cylinder, that's pi radius squared, and then it has a length of L, so let's say pi radius squared L. Okay, but then we can also express this in terms of our elementary mass. Okay, it has a mass of dm, so our element is the one in green, so that's dm, the mass of the element, divided by the volume of the element, which is just pi radius squared times dz, which is the thickness. So we can write already that dm, okay, is just so these things would cancel out, so that's going to be m on capital L times dz. So this is the mass, this is our elementary mass. Okay, so now what we need to do, since we are interested in calculating Ix and Iy, we need to make use of the perpendicular axis theorem. If you recall, we stated that in a previous video. If you haven't watched it, you can go and watch the introduction to this video series on moment of inertia, and I explained all the essential things to be known about moment of inertia, including the parallel and perpendicular axis theorem. So here we are going to make use of the perpendicular axis theorem. I'll just put it in green. So perpendicular axis theorem. Okay. Okay, so how do we apply that? You're going to notice that on my diagram, I actually have two sets of axes. I have a first set of axes, okay, that is centered about the center of the cylinder that you can see here, O, and I have another set of axes that's centered about our elementary mass, our element, which is x prime, y prime, and z. Hope you can see that. It's important to distinguish between these two in order to appropriately apply the theorems. So the perpendicular axis theorem applied to this disk tells us that Iz, so the moment of inertia of the disk about the z-axis, is going to be Ix prime plus Iy prime. Okay? Remember that to apply the perpendicular axis theorem, we need one axis and a pair of axes that are perpendicular to each other and to the third axis. So just like the right hand rule, you have two axes and you need a third that's perpendicular to the other two axes. That's why we need x prime and y prime. Okay. That being said, ix prime, of course, has to be equals to iy prime, again due to symmetry. Don't remember if it's 1m or 2m anyway. So we can already see here that that ix, okay, that ix prime is going to be iz over 2, and this is also equal to iy prime. Hope that's clear, because ix prime is iy prime, so they are both equal to half iz on 2. Okay. But then, if you recall, iz is just the moment of inertia of the disk about an axis perpendicular to the plane of the disk, and that passes through the center. And we saw that in a previous video. You can also go and watch it, how to derive the moment of inertia of the disk, because I want to do it here. So I of the disk, we saw that it was just half the mass times the radius of the disk squared. So we are going to make use of that result. We plug it here. We are going to have iz as, so we are going to have iz as the mass. So half times the mass dm times the radius squared. So half r squared dm. Okay. Later on we are going to integrate. Actually, I could have called this diz just for clarity. Okay. We can call that diz since we are dealing with dm, so that things should be clear. All right, so here we have diz, okay, which means that dix, okay, dix prime, which means that dix prime is just going to be half of this quantity, so 1/4 r squared dm. Okay. We're going to perform integrals later. So this is the moment of inertia of this element about the x prime axis. So it's an axis that passes through its center of mass, this point, okay, and that's perpendicular to the main axis of the disk, so the z-axis. It's really important to understand this first step. Then we are going to make use of another theorem, this time the parallel axis theorem, in order to calculate ix. You can clearly see on the diagram that ix prime is parallel to ix, so we can clearly apply the parallel axis theorem. So parallel axis theorem, okay, which in this case tells us that the moment of inertia about the axis x, so ix, okay, we can call it the ix since we are dealing with the mass, the elementary mass dm. So the ix is going to be the mass, is going to be the moment of inertia, okay, of the disk about its center of mass, so ix prime, so we're going to call it the ix prime, plus the mass of the disk times the distance between the two axes, the two parallel axes, which in this case is z, all that squared. Hope this is clear and that you can clearly see that this is the application of the parallel axis theorem. So we can write it in a more explicit way. So that means that dix actually is this quantity, 1/4 r squared dm plus z squared dm. Okay, hope that's really clear. So now what we can do if you want to get ix is just to integrate all this expression. So ix, okay, it's just going to be the integral, okay, over the mass of this whole expression, so 1/4 r squared dm plus z squared dm. Okay, so we just need to calculate this expression to get ix. So let me take another sheet of paper. So then we have Ix, which is equal to the integral of 1/4 r squared plus z squared dm. But then if you recall dm, we know its expression. So dm is just capital M over capital L times dz. Okay, so M on L dz. We can replace that here. We're going to have Ix as the integral of 1/4 r squared. Okay, so I can put the constant outside of the integral, so M over L 1/4 r squared plus z squared, then dz. And then the boundaries of integration, the bounds, and then the limits of integration. You can check that here. You can see that we need to integrate from negative L over 2, okay, to L over 2. So from here, negative L over 2 to L over 2, so that we can generate the whole cylinder. So we need to move this disk all through like that, from negative L over 2 to L over 2. Hope that's clear. So here we have negative L over 2, and here we have L over 2. So you then need to perform this integral. So we have here M over L. Here we're going to have, I'll just write the result. That's really straightforward integral. So r squared. Here we're going to have L plus, here we're going to have L cubed over 12. Here we're going to have L cubed on 12. Okay, because you have z cubed on 3, then you apply the bounds. You have that over. Okay. All right. So we get. So if you simplify that, we're going to have 1/4. Okay. M, the L's cancel here, r squared plus L cancels here. We're going to have 1/12 M L squared. So this is the moment of inertia of a cylinder about an axis passing through its center and perpendicular to the central axis. You can put that in the box. Okay. So axis through center. Then we can go further and calculate the moment of inertia about an axis that passes through the end of the cylinder. Okay, if you want to do that, we can just it's just an application of the parallel axis theorem again. So suppose we want to calculate I about a new axis that passes through the end of the cylinder. Okay, we can do that. It's really easy. We just apply the parallel axis theorem once more. So I about the n, let me say that like that, would just be I about the center plus the mass times the distance between the two squared. So that's just going to be L over 2 squared. Okay. So if we simplify this, we're going to have that IN is just going to be I center, so this 1/4 mr squared plus 1/12 ml squared plus L squared over 4. So we're going to have that IN is just going to be, so that's 3/3, so that's 1/3, so that's 1/4 mr squared plus 1/3 ml squared. Okay, it's really straightforward application of the perpendicular axis, of the parallel axis theorem, I mean. Okay, so hope that's clear. If you have any questions, feel free to ask them in the comments. Okay, or if you have any remarks, feel free to point them in the comments. Okay, see you in the next video.